Hello everyone, my name is Christelle Piechurski and I'm Chief HPC and Quantum Officer at GENCI. And among my different missions, I am in charge of coordinating the National Technology Watch Group, also known by some of you as CVT or in French, Cellule de Veille Technologique. Today my talk will provide an overview on how the French research community is assessing new technologies, focusing on how this community has contributed to the HARM ecosystem along the last 10 years, both at European and national level, to support the post-one Exascale system that matches with large-scale scientific challenges. For those who don't know GENCI, it stands for Grand Équipement National de Calcul Intensif. We have a French national agency in charge of procuring innovative and performant computing resources and massive storage capabilities to sustain the French academic and industrial open research, both in numerical simulation and converged HPC and AI. We have been created in 2007 and our main shareholders are the Ministry of Higher Education, Research and Innovation, the CEA, which is the French Nuclear Agency, the CNRS, INRIA, and the 74 French universities. We have 3 national supercomputers to support French research. 2 are hosted near Paris and operated by CEA and IDRIS, and 1 is hosted in southeast of France and operated by Sines. They do provide a global capability of around 2 billion computing hours per year to sustain users' needs for around 1,300 projects in total, among which more than 700 projects in artificial intelligence and 600 projects in high performance computing. And the way we procure our system is supported by the National Technology Watch Groups, as these systems we are buying are generally not available on shelves, and we use that vehicle to prepare the acquisition of our future machines, and also to prepare the application owners to understand what are the efforts to engage efficiently to use the states of the art resources. And the last point, we are strongly engaged in the European ecosystem through PRACE as one of the 5 hosting members, with a Joliot Curie supercomputer used as a tier 0 machine. The Technology Watch Group, which partners appear below, has been created in 2006 at the time where some exotic technologies like many cores or GPU arrive on the market. And we realized that we will need to engage with users to understand the potential of these technologies and understand what were being forced to engage to adopt those new solutions. And in the diversity of what we see in the HPC and AI ecosystem today, this vehicle is more and more crucial, even though we can't address all topics, but mostly the most promising ones. As I previously mentioned, the purpose is really to prepare national centers by anticipating what could be the future architecture to leverage and what efforts need to be done to assess hardware, middleware, software ecosystem maturity, and also make sure application will be ready once a technology will be adopted massively. For this, we are working with a set of around 20 applications in various scientific domains. We are also acquiring prototypes which are installed in our national facilities, or we access remotely some technologies. And more important than everything, we collaborate with partners and chip suppliers by exchanges our mutual expertise. Right now, we have done this with 3 prototypes already, which led successfully to 3 large-scale deployments onto Joliot Curie for the Caenel technology. On GENCI, the machine deployed today with more than 2,700 GPUs addressing both HPC and AI. And the last one was the Sander X2 prototype available in TGCC, which has led to a deployment of the HARM A64FX system in production since June this year. There are several step applications on our performing, probably the same way like some of you are doing. For sure, we invest in code portability. We also compare run some comparison node to node with existing and well-known technologies we have deployed on our own data centers. We perform optimization. For sure, we look at the scalability of the code, and we also inject code modernization if needed. And last point, but not the least one, is we look at energy efficiency of the technological solution to assess. And this is clearly in line with the way we are driving our national procurement by focusing on full-fledged application efficiency at load, energy efficiency at load too, and for sure the total cost of ownership of the chosen system. Now, if we look at how far we have come on HUM, we have to look 10 years behind us when we started to participate with BSC to the Mont Blanc project. This was in 2011, and we were already convinced that HUM could be a processor which could fit HPC workloads. At that time, we have been involved in the co-design program by providing inputs on 11 applications, which are currently running either on Tier 1 or Tier 0 systems, among which you can find SPEC-FM 3D, which focus on simulating 3D seismic wave propagation, and also Big DFT, an application on electronic structure, mainly used in the domain of structure prediction calculation, which are also applications that we have pursued our effort in the scope of the EPI co-design. So the purpose was also to define the HUM software ecosystem, has understand how the technology could help on energy efficiency, which is one of the major stakes for HPC, and moreover, extremely large scale system as Exascale and Exascale ones. Since 2008, our community is also partnering in EPI and involved on application designs in the SGA1 project, mostly on Big DFT, AVBP, Gisela, SPEC-FM 3D, and for sometimes on NEMO to provide inputs on code programmability. And this project mainly aims to build IP for the first chip design of a general purpose European processor and understand features to implement like vector instruction. So our community is now pursuing its commitment to EPI in the second European project called SGA2, which will mainly target the design of a second general purpose European processor. And we are now part of the UPEX consortium for the Horizon 2020 project. The consortium gave us more than 15 European partners, and its major target is to design, build, and deploy a modular Exascale pilot system to leverage several European technologies, among which you would find the European general purpose processor from EPI and commercialized by Cypel, the European interconnect technology from Atos based on BXI, and the European software stack for HPC. This will be a 4-year project to demonstrate the readiness and the scalability of the pilot technologies and prepare European application and prepare users to efficiently exploit those technologies. All together, the first phase of the UPEX project will rely on a series of in-kind system providing by partners, and the A64FX system from GENCI and CEA will be the most advanced system to support application porting and optimization as software ecosystem design until the REA processor from Cypel will be ready to be integrated in this pilot. And for sure, this is a key project for us, as the successful achievement is a major step to reach and demonstrate confidence for European instances to invest at least in one European Exascale system based on European technologies in the coming years. The project should start by very early 2022. At national level, we have been acquiring several ARM prototypes since ARM processors are available on the market. This has provided us a capability to participate in the various co-design projects I have just mentioned about. In addition to the physical prototypes we organize several events like workshops or hackathon on different thematics to support our users to engage on ARM with the help of experts from ARM and Atos, and also with the help, the huge help of the support team from the data center facilities. Both actions are initiated and coordinated through the National Technology Watch Group. For a ARM assessment, we initially started in 2008 with 4 ThunderX2 nodes in which we have invested. Each one was with 64 cores running at 2.2 gig. The community has focused on porting 15 applications on this technology. And one straight outcome of the first hackathon was that most of this code were successfully ported after less than 1 day. And we were able to execute all the application for sure without any optimization on the ARM ThunderX2 nodes at the end of these 2 days of hackathon. We also ran some comparison node to node with x86 nodes based on Skylake processor, where we demonstrate performance improvement benefiting to memory bound applications like NeMo and MISO-NH. And in many cases, we sorted out that there was a one-to-one comparison in time to solution between the Marvell ThunderX2 nodes and the Intel Skylake nodes, which is a quite great performance achieved. In March 2019, we decided to invest in a larger Marvell ThunderX2 system with the same processor than the previous node acquired earlier. The platform is relying on an Atos Sequana XH platform with 30 dual socket nodes based on ThunderX2. And this has allowed us to go further in testing and the scalability of the application on a second hackathon, where we have been able to demonstrate a great efficiency for most of the application up to 16 nodes, the number of nodes that were available at that time. And finally, we ran a third ARM hackathon, which was organized late February 2020, to learn a bit more on SVE, the scalable vector instruction. We perform an extended dynamic instruction analysis for various full-fledged applications with a strong support of ARM. I'm not going to go further in describing all the results, but you'll find all these result details on the ARM community blog if you follow the link that you would find on the left bottom of this slide. Finally, as I previously mentioned, in October 2020, we acquired an 18 nodes Fujitsu cluster through Atos to install as a 5th partition of the Joliot Curie Tier 0 supercomputer. And this acquisition was done in the framework of PPI for HPC. The Fujitsu partition is an exploratory system which is integrated in a full production environment with access to the same shared level 1 and level 2 storage file system based on Lustre, has the over 4 partitions of the Joliot Curie supercomputer. And the main purpose of this partition is to pursue the efforts that we already engaged since a few years to evaluate ARM characteristics more in line with the future European general purpose processor, which will also have some technological characteristic like HBM and SVE capabilities. The A64FX system has been opened in June 2021 for early access to 20 users working on 10 different applications, mainly for sure our usual suspects. A workshop with around 35 attendees has been held the 3rd week of June to transfer knowledge to the users from low-level microarchitecture of the A64FX processor on how to use the various compilers accessible on the machine to efficiently exploit the benefits the design of a processor. You may have the opportunity to follow a job done on Smiley run by Mathieu Lobet and his team from La Maison de la Simulation. He is also going to normally introduce its results during the AHUG symposium for SC21. And Atos Ham4G will have provided us support on this workshop, and we open with confidence the machine to a broader audience October the 1st, before we will open it to the European community through PRACE and UPEX users early 2022. So this was mostly what I wanted to share with you, and I'm glad to take all questions afterwards by email if you want to discuss the talk with me. And I also want to thank Harm and my colleague in the Harm HPC User Group Board of Directors, who are doing a great job on the AHUG SC21 symposium. I wish you all a fruitful SC21, and I hope to see you there in person next year.